Hello, this is Dr. Michael Hassan, the engineering doctor, and this is lecture number 34, the D flip-flop of chapter 6, flip-flops of the course Digital Logic Design or Digital Systems of Digital Electronics. This is a disclaimer for you to read. I cite 3 references, however, there are many books in digital logic design. Chapter 6 contents include sequential networks, memory elements, the SR flip-flop, clocked SR flip-flop, the JK flip-flop, the T flip-flop, and in this lecture we will talk about the D-type flip-flop. The D stands for delay. Flip-flop has one input denoted D and 2 outputs denoted Q and Q prime. The next state output Q plus after applying a clock pulse equals to the input D before applying the clock pulse. So the value of D will transition from the input to the output after applying a clock pulse. Therefore, the data bit is delayed by 1 clock cycle. The D flip-flop, if a JK flip-flop is modified by the addition of inverter as shown in figure A, so D will be equals to J and K will be equals to D prime, or the complement of D. Okay, the resulting device is a D-type flip-flop. From the JK flip-flop, the truth table, Q plus will be equal to 1 for D equal to J equals to Q prime equals to 1. And Q plus is equals to 0 for D equals to J equals to Q prime equals to 0. Hence, Q plus equals to D. So based on the characteristic equation of the JK flip-flop, JK flip-flop characteristic equation is Q plus is equal to J Q prime or K prime Q. So if I replace J with D, so you will get D Q plus will be D Q prime or D Q. So you take D as out as a factor, so D Q plus will be equal to D factor out Q or Q prime, which is equals to 1, which is equal to D. So simple proof of the characteristic equation. So you can look at the truth table of the J flip-flop as we have seen here, and Q plus will be equal to D, which is the characteristic equation of the D flip-flop. So based on this, so we have the D flip-flop using JK flip-flop. This is the symbolic representation, the block diagram of D-type flip-flop, and B, the truth table and the compact truth table. So when we have D00, 0, whether Q is 0, 1, the output will be 0, 0, and 1, 1, whether the Q is 0 or 1, the output will be 1, 1, which is a Q plus. So Q plus is always equals to D. So if you look at this column and this column, they are the same. 0, 0, 1, 1, D 0, 0, 1. So the output basically will be equal to the input delayed by 1 clock cycle. The compact D and Q plus, if D is 0, Q plus is 0. If D is 1, Q plus is D1. So this is the truth table of the D flip-flop, and this is the compact table of the D flip-flop. So based on this, we can have the transition table, the transition requirement table, or the excitation requirements table. Q to Q plus 0 to 0, D will follow Q. 0 to 1, 1, 0, 1, 1. And D precisely will be equal to Q. So it gets 0, 1, 0, 1. So again, the state graph, we have 2 stable states, state 0 and state 1. And the value of D, if we are remaining in state 0, 0 to 0, D has to be 0. See this arrow, it means we are remaining in state 0. If we are going to state 1, we need D to be 1. 0 to 1, I need D to be 1. If I am staying in state 1, 1 to 1, D has to be 1. And if I'm going back to state 0, D has to be 0. 1 to 0, D has to be 0. So the state graph is graphical representation of the excitation requirements table shown. Now, we have proven the characteristic equation of the D flip-flop, which is Q plus is equals to D, based on the characteristic equation of the JK flip-flop. We have proven the truth table and the compact table, and we have shown the excitation requirements table and the state graph of the D-type flip-flop. Now, the timing diagram for an assumed D and Q and clock pulses, we see the timing example, the D-type flip-flop. At the negative edge, D is 1, initially Q is 0, and there is D. At the negative edge, okay, D is still 1, and Q will change state from 0 to 1, follow the value of D. At the next negative edge, D is 1, D is still 1, so Q will continue to be 1, because Q plus is equals to D. At this edge, BCD went to 0, so is the Q plus. So Q plus will be 0, so you find Q is 0, which is equal to 0 on the next negative edge. It's quite simple. Hence, the falling edge of the third clock cycle pulse, hence the output Q switches to 0, and I put this literature for you as well. Okay. The next slide will show us a 6 NAND gate positive edge trigger D-type flip-flop without using a master slave. Master slave is an excellent flip-flop, but it's pricey. So someone came with this design, and this design with a preset and clear, and using 6 NAND gates. We assume that preset and clear are not accepted, hence the clock 0, Y1 and Y2. This is the output Y1 from gate 2. You get Y1, Y2, and Y3 and Y4, okay? And the upper NAND, 3-input NAND gate, and the very lower NAND gate number 4. Okay, so we have Y1 equals to Y2 equals to 1 when the clock is 0. Now, when the clock is 1, therefore the output latch is in the hold mode that Q plus is equals to Q. When the clock is 1, the values of Y3 and Y4 are transmitted through gates 2 and 3 to cause Y1 equals to D prime and Y2 is equals to D, which set Q plus is equal to D, and Q prime plus is equal to D prime, which is the characteristic equation of D flip-flop. To operate unfailingly, the values of Y3 and Y4 be stable, while the clock changes from 0 to 1. Hence, the setup time of D flip-flop is equal to the delay from D input through gate 4 and gate 1 to Y3. The hold time is given by the delay of gate 3, since once Y2 is stable and changes in D will be ignored. So this is a simple description of this 6th NAND gate, since NAND gate D-type flip-flop, and it is positive edge triggered. It is an excellent invention, an excellent replacement for the master-slave design of a normal flip-flop based on the JK flip-flop. Now, this is actually the last slide. I would like to thank you so much for listening. Please subscribe by clicking on the blue circle. Give me thumb up, so we'll give you more beautiful lectures. And hopefully I will see you very soon in the next lecture. Sincerely, Dr. Hassan.